So in last class we were discussing about the equivalent circuit diagram of a practical transformer, and we have tried to shift the secondary side parameters onto the primary side parameters, and then we have shown the phasor diagram for the transformer for no load operation and on load operation. Okay, so we will further extend this topic. E1 equals to E2 dash, and this voltage here is V2 prime, right? So this is an equivalent circuit of a transformer referring the secondary side parameters all onto the primary side, right? Similarly, you can also represent the primary side parameters onto the secondary side if required. You may be asked to refer the transformer parameters onto the secondary side completely. Then same logic works out, right? So in transferring the resistances, the I square R on primary side should be equals to the secondary side equivalent currents. The power losses should be same. In transferring the reactances, the voltage drops. I1 x1 by E1 should be equals to I2 x2 by E2. So based on this logic, we can similarly transfer the primary side onto the secondary side. So if I draw the now here the R2 dash is equals to A square times actual R2, and x2 prime is equals to A square times x2, and E2 prime is actually is equals to A times E2, and I2 prime is I2 by A. These are the relationships, right? These are the actual secondary quantities. These are the primary side referred quantities of the secondary, right? Now similarly, if I draw the equivalent circuit diagram for the transformer referred to the secondary side, then I will be having same diagram, but parameters will be referred to the secondary. Now this voltage will be as it is V2, this voltage will be as it is I2, this is R2, this is X2. Now this voltage here will be E2 equals to E1 prime. Now E1 is referred to the secondary side. Similarly, all these parameters will be referred to the secondary side. This is R1 prime, X1 prime, this is RC prime, this is XM prime, and this is I0 prime, IL prime. All parameters will be IMU prime, and this is I1 prime, and this voltage now will be V1 prime. Okay, so what we have now, onto primary referred to the secondary, reverse of these things, right? So it will be by, so let me write down now, this is R1 prime is equals to R1 by A square, and X1 prime is X1 by A square. Similarly, these two parameters as well, RC prime is equals to RC by A square, XM prime is equals to XM by A square, resistance and impedance values. Whereas the voltages E1 prime is equals to E1 prime is equals to E1 by A, and I1 prime is equals to A times I1, reverse of the secondary side components, right? So this is how the parameters can be shifted from primary to secondary, secondary to primary. Okay, now there is one more. Normally we term the transformer turns ratio. Now till now we have defined A is equals to N1 by N2. This is transformer turns ratio. Okay, now sometimes in some books they also called as transformation ratio. They use transformation ratio, which is actually defined something like N2 by N1, now which is reciprocal of A, which is transformation ratio of the transformer is N2 by N1, which is actually the reciprocal of what we have defined A, right? So all these, if someone gives you transformation ratio, then you can convert it into turns ratio and then use the same formulas, or otherwise you can also define all these parameters, all this conversion in terms of, if I define 1 by A is equals to K, then you can rewrite these transformation equations in terms of K as well. So if I replace A by 1 by K square here, A square is equals to 1 by K square, so these equations will become in terms of transformation ratios, right? Okay, that's it. So only remember only one formula, just you know that transformation ratio and the turns ratio are just reciprocal to each other. That's it. Now let us proceed further. Normally the transformer equivalent circuit, this circuit is very not so frequently used, because here it increases one node. This is input node, and this is output node, and this node increases one more. Yeah, so that is why what they do is they shift this T limb to the input side node, right? So we can draw the approximate equivalent circuit is something like this. So if I keep the ideal transformer here, ideal transformer, okay, there is no connection here. This is ideal transformer. This is now R1 X1, this is R2 X2, this is E1, this is E2, this is RC XM I0, and this is I1, this is I2, and this is V1 V2, right? Now without removing the, or without bringing these parameters onto the one side. Okay, now this can be referred, these secondary parameters referred to primary. We can draw the equivalent circuit r1 x1, this is r2 dash x2 dash, this is again same rc xm, this is I naught, this is IC or IL, this is I mu, and this is V1, and here we have E1 is equals to E2 dash, and this is V2 dash. Now what is this? Now I can say these two values are equivalent, and these two values x equivalent referred onto the primary. So all parameters referred onto primary, right? And if I suppose show it onto the secondary, still the circuit diagram looks like same, only the parameter values calculated will differ. Okay, so this is V2 now, this is R2 x2, this is r1 dash and x1 dash, primary side values refer to the secondary. This is rc dash, this is xm dash, and this is I1 dash, this is I naught dash, this is IC dash or IL dash, this is I mu dash, and this is I2, simple I2, and this voltage now is equals to E1 dash, which is equals to E2, and this is V1 dash, right? So here in this case we know that the R2 dash is equals to a square R2, and x2 dash is equals to a square R x2, where a is n1 by n2, right? And E2 dash is equals to a into E2, and I2 dash is I2 by a. Yeah, this is particular to this one, and here in this case this is I1 dash referred onto the R1 dash is equals to R1 by A1 square, x1 dash is equals to x1 by A1 square. Okay, and what else we also have? This is RC and XC. XM dash is equals to XM by A square, and RC dash is equals to RC by A square. Similarly, we also have currents and voltages. E1 dash is equals to E1 by A, and I1 dash is equals to A times I1. So these are all the relationships transferring from primary to secondary and secondary to primary, right? So this is the equivalent circuit normally which we prefer in calculations, right, to eliminate the extra node. Now this node is nothing but the input node, both are same. So we have here only two nodes. Now let us discuss about the losses in the transformer. Right? So so majorly the two types of losses takes place in the transformer, that is core losses and copper losses, right? So again, core losses divided into hysteresis losses and copper losses simply I square R losses, right? Now these losses are accommodated in the circuit diagram. Let me take the exact circuit representation of the transformer, but all parameters onto the primary side. Okay, so the core loss component is shown or represented in the equivalent circuit by the RC component, right? So what all losses taking place in the core, that is hysteresis losses and hysteresis losses and eddy current losses, both taking place in the core, are represented by this limb, RC limb, and copper losses, this is I1 square R1 and I2 dash square R2 dash. They are represented by the equivalent resistance in primary and secondary resistance values, right? And the magnetizing current component is shown by the I mu or Im, right? So what I want to say is, so these hysteresis losses, if you hysteresis losses is proportional to B to the power of 1.6 for an iron core multiplied by F, and eddy current loss is proportional to B square F square. Okay, now I can say we know that this induced EMF is equals to or proportional to 4.44 phi F and number of turns, right? This is proportional to. So if I represent this flux in terms of B, right? So this is proportional to B times A F N, right? So what is B here? I can say B is actually B is proportional to E by F or approximately V by F. Both E and V are almost same. So this is B is proportional to V by F. So the flux density in the core is proportional to V by F. Now in this case, if I substitute this B here, that is hysteresis losses is proportional to V by F times 1.6 by F, and eddy current losses are proportional to V by F whole square into F square. So in this I can say now this is approximately, if I cancel this and this one and this and this one, so these both losses are function of the supply voltage, or function of eddy current loss is function of V square, and hysteresis losses is function of V to the power of 1.6. Okay, so if keeping the supply frequency constant, and vary the magnitude of the supply voltage. So how does it affect? by varying the supply voltage, the eddy current losses and hysteresis losses. Altogether, I can say that the entire core loss is proportional to V square approximately, right? So if unless and until the supply voltage is also not changed, then core losses in the machine remains constant. But if supply voltage changes, then core losses changes by square times. So I can say these two terms until there is no change in frequency and supply voltage magnitude, core losses in the transformer remains constant, and which is remains constant, and it I can say which is independent of load. Any load, for any load condition, it will remain constant. But if supply voltage magnitude changes, then core losses will change according to according to V square times, right? So yeah, this is all about the core losses as a function of supply voltage and frequency, right? Now what we can say is, when the under two extreme conditions, that is conditions, one is no load and other one is under short circuit conditions, right? So under no load condition, see the transformer equivalent circuit this is open, and there is no I2 dash or I2 current. So this is now I1, which is actually a component of I0, this component, plus I2 dash. Now this component is 0 and this component is 0, right? So now this I1 is almost equivalent to I0, and this I0 is very small, or very small as compared to the rated current of the transformer, Typically it will be around 1 to 5% of the rated current. Now under that conditions, the watt-hour power input into the transformer under no load condition is mainly contributed towards the core losses, right? So because this I0 square R1 is far less than I rated square R1, right? So that is why the primary copper losses are neglected, and all power input into the transformer is consumed towards the core losses, right? So this is one thing we came to know, that under open circuit all power input into the transformer is consumed towards the core losses. Okay, now the other thing is, under short circuit condition, right? Now this is fed with this this is fed with this supply voltage, but this secondary is short circuited, right? The secondary is short circuited. Now under this condition, normally we try to manage the supply voltage such that the rated currents will flow into the transformer, right? Now under this condition, because it is a short circuited onto the secondary, I can say that very less magnitude, that is approximately 5 to 10% of rated voltage is sufficient to circulate rated currents in primary and secondary. We know that in the transformer, whatever there is a secondary ampere turns, then it is drawn from the same amount is drawn from the primary side. If it may be a load or it may be a short circuit, whatever may be, the ampere turns drawing from the secondary terminals is consumed back or compensated back in the primary side by a equivalent ampere turns. If this is N2 I2, then the corresponding N1 I1 ampere turns is drawn from the source, right? So the secondary equivalent, what all the copper losses taking place in the secondary is, if I measure the power input under this condition, then this power indicator, that is wattmeter, will also show the secondary side copper losses, right? Now what about the core losses under this condition? As just now I said, the core losses is proportional to V square, right? So to obtain the rated current on primary and secondary, only 5 to 10% of the rated voltage we have applied, right? So core losses is reduced by almost 90%. So it will be 0.01 of that of rated core losses. Okay, so that is why under short circuit condition we assume that all the power input under this condition feeding into the transformer is consumed towards both primary and secondary copper losses. Right? And we neglect this reading. Under this reading only the copper losses are measured, but not the core losses. We neglect the core losses. Okay, so under these two extreme conditions, we came to know that the reading of the wattmeter under open circuit condition measures the total core losses, and which are actually constant throughout its operation until and unless supply voltage is not varied. And under other extreme condition, under short circuit condition, we came to know that the wattmeter reading measures the primary and secondary I square R losses, but though there are very small fraction of core losses, we neglect that. Okay, so to actually knowing these two concepts, then we can find out or determine the equivalent circuit parameters through these two tests. Okay, so in OC test, what we do is we connect one voltmeter, one ammeter, and one wattmeter. Yeah, let me show here. This is a wattmeter. Okay, and this is kept open. This is kept open, and we measure the values, voltmeter values, current values, and wattmeter values. That's it. We have these three values, right? And from these, what we know, the power input is equals to VI cos phi. From the phasor diagram, this is V, this is phi, and this is the no load current I naught, which is having two components. One component is IC component and one component is I mu component, and this is no load power factor, right? So the power input is equals to V magnitude I magnitude cos phi. So from this, cos phi is equals to power reading divided by voltage into current. So once we have the cos phi, so I can find out the angle cos inverse of P by VI, right? So I know the power factor angle, I know the input current, no load current. So this is no load current, right? So the I naught cos phi component is IC. I naught cos phi component is IC, and I mu is I naught sin phi component. So I can now calculate the core loss component of current and magnetizing component of the no load current. So once I know these, then I can calculate the branches, these values. Yeah, so either I can also say that this component, power loss component, is equals to IC square RC, or RC is equals to P by IC square. Yeah, neglecting the primary copper losses, or otherwise one second. Yeah, and this is RC, small RC. Okay, and What about XM? XM I can directly find out VM or V by IM. V by IM or V by I naught sine phi component. Okay, so I from these measurements I have calculated the IC component of current, I mu component of current, and RC and XM. So these two values are determined, and this current are determined from the no load test. Now in short circuit test, yeah, so here what is that actually we do is in no load test, because we need to apply rated voltage. This is rated voltage, right? Normally LV side we prefer to keep the meters, and HV side is open, so that the rated low voltage is obtained through some variac. So we keep some variac here, okay, and we try to bring this variac voltage to rated value and then take the readings. So normally these values the meters measuring instruments are kept on LV side and HV is open. That is what we need to know. Now in case of short circuit test, now this is shorted, and similarly we keep ammeter, one voltmeter and one wattmeter. Okay, so this is a variac. Now, yeah. So now this SC test, short circuit test, normally meters are placed on HV side and LV is shorted, right? Why HV? Now we need to conduct the primary with rated current on this side and this side. Okay. Now under short circuited condition, this rated currents will flow for small percentage of voltage, that is approximately 5 to 10% of V rated. Okay, so as I said, under short circuit condition, whatever may be, the secondary side ampere turns will be compensated equivalently from the primary side with equivalent primary ampere turns, right? Now because we are applying or we are getting the rated current for 5 to 10% of rated voltage, the magnetizing current component and the loss component are very small, because as I said, core loss is proportional to V square. So V is reduced to 5 to 10%, so core losses will reduce by square times. So that means core losses are almost neglected. So this component, IC component, will goes to very small value, and also the IM component, magnetizing current component, is actually also goes down. So entirely under short circuit condition, this limb is can be neglected or removed, right? So what all wattmeter reading goes into these primary and secondary copper losses. So what we do is we remove this limb, right? And the equivalent circuit under this condition, the short circuit condition, is treated like this. Okay, so we measure the rated current on primary side, we calculate, and we try to adjust the supply voltage till the rated current, and voltmeter reading will measure, and wattmeter reading will measure. This is pre-calculated. This value is pre-calculated, and this is adjusted till this rated current is obtained, and all the 3 meter readings are now taken. Now from this, what we can know, so this total impedance Z equivalent, right? Meter does not know what is primary and what is secondary. It sees some impedance onto the transformer. So this is actually R1 plus R2 dash plus J X1 plus X2 dash. So total impedance is seen. So I can calculate this equivalent impedance referred to the HV side now. These values are referred to HV side. Earlier what we have obtained here, these two shunt limb elements are actually obtained onto the LV side. These values are on LV side. Okay. Now Z equivalent is equals to simply the voltage, the short circuit, whatever the short circuit voltage we have applied, divided by the current. This is the short circuit current, rated current or short circuit current, whatever it may be, right? So this ratio gives me the total impedance, and from power calculations, the short circuit power is consumed towards the short circuit current square and R equivalent, right? Where R equivalent is actually R1 plus R2 dash. Okay. Now from this R equivalent, I can calculate P short circuit value by ISC square. So I have calculated the equivalent combined resistance, and I have calculated the combined impedance, right? So where Z equivalent is equals to R equivalent plus J X equivalent. Magnitude wise, this can be written as Z equivalent square is equals to R equivalent square plus X equivalent square. So from this X equivalent is equals to root over Z equivalent square minus R equivalent square. So we can get the magnitude of the reactance, but we don't know the actual components. What are these? R equivalent is equals to R1 plus R2 dash. We cannot segregate these two. This is together we got. And similarly X equivalent is equals to X1 plus X2 dash. Together we got the value, but we don't know what is what, which value is which one. So if in problem they mention some ratio, primary side 40, 60, like that. If 50, 50, then accordingly you divide these value among this R1 and X2 dash, right? Normally this ratio is mentioned. Okay, now from these two tests, in OC test we got the parameters onto the LV side, and in SC test we got the parameters, these two parameters onto the HV side. So you have to convert the R equivalent and X equivalent from HV side to LV side. Okay, and then you have to convert, right? So yeah, so I don't know if same, this is LV and this is HV, and this is N1 and this is N2, N1 and N2. So we know N1 by N2 is equals to A. Now these two parameters on HV side, so bring on to LV side. So LV side, this is R equivalent dash is equals to A square R equivalent, and X equivalent dash is equals to A square X equivalent, right? Now once we get these parameters, then I can simply draw the complete equivalent circuit. Yeah, initially I don't know this, I know only one, R equivalent dash X equivalent dash, this is RC and XM, this is actually the LV side, and this is HV side. So this is V2 dash, this is V1, and this is I1, I2 dash, and this is I0. So if they give any proportion, then you can divide this one according to that proportion. R1 plus R2 dash, and this is X1 plus X2 dash. So you have to divide those values, right? So this is all about the losses of the transformer, how they can be determined from open circuit test and the short circuit test. Now if I want to calculate or define the efficiency of transformer, so this is output power by input power, straightforward equation, right? So now output transformer may be loaded at any loading condition, so I can now if I define the iron loss component by core loss or iron loss by Pi, which is actually a constant throughout the operation, and PC is the copper loss at full load condition, right? Now if I want to calculate copper loss for any other load condition, how should I represent in terms of this one? So I can say X square times PC will be the copper loss at X percentage of the rated condition. What is S? S is the volt ampere rating. V rated, I rated, the actual rating of the transformer either in kVA or in MVA, right? And X is the percentage loading. Percentage loading means the current loading. X is actually the actual current by the rated current. Okay, so at this percentage of loading of the transformer, the copper loss will be X square times the actual copper loss at full load. Now I can say the output is X times the rating multiplied by this volt ampere rating multiplied by the cos phi divided by the output plus losses, that is X times S into cos phi. This is output plus losses. What is the losses? We have two losses, iron losses and copper losses. So iron losses will be same for any loading condition, plus copper losses is where is X square times the rated copper losses of the machine. So this is the efficiency formula. Now to have the maximum efficiency condition, then I have to take the derivative of this efficiency with respect to the loading condition and equate it to 0. Okay, so which implies I can say X into S into cos phi. I am taking the derivative plus Pi plus X square Pc, this whole term multiplied by S, derivative of X, S cos phi, so that is S into cos phi minus numerator X into S into cos phi into derivative of the denominator. Derivative of the denominator will come to S cos phi plus 0 plus 2 times X into Pc divided by the entire numerator square equals to 0. That is what we get. Now if I equate it to 0 and do some simplification, so this is X into S square cos phi square plus Pi S cos phi plus X square Pc S into cos phi. I am multiplying this, expanding. E is equals to, I am bringing this second term onto the right side, X S square cos square phi plus 2x square S 2x square S Pc cos phi. Is it right? Now I can cancel out some terms. So this term and this term entirely goes out, and this x square PCS cos phi 2x square PCS cos phi. So I bring out this term onto the right side. So I have PIS cos phi is equals to, so one term goes out, so this is x square S PC cos phi. Okay, so I can cancel out 1s cos phi. So I have x square is equals to pi by pc, or x is equals to pi by pc. So the load at which maximum efficiency occurs is given by that is x is equals to root over pi by pc. So what are pi and pc? Pi is core losses and pc is full load copper losses, or otherwise I can say that this is x square pc from this x square pc is equals to pi. So x square pc is the copper loss at that particular loading condition. So this term is copper loss at this particular loading condition. Now, so the maximum efficiency at which that particular loading condition, the copper losses are equals to the iron losses. I can also say in that way. So this is about the efficiency formula and the derivation or condition for maximum efficiency of the transformer. So this is the efficiency output by input. Okay. So we'll stop here.